Alright, so this tutorial, this part of the discussion will be all about questions from Kirchhoff's law. Okay, questions from Kirchhoff's law, and these questions are based on past papers and department prototype papers as well. Alright, first we start with 2016 prototype paper, and let's see how we are going to apply the Kirchhoff's law for this. First question. As shown in the figure, the value of the resistance of capital R in ohm for the ammeter reading to be 0. So, they have given you an ammeter here. They have given you an ammeter, and they are saying the ammeter reading is going to be 0. The ammeter reading is going to be 0. So, there shouldn't be any current flowing through this path. There shouldn't be any current flowing through this path. I think this question is going to be very simple. If there is no current flowing through this part, if the ammeter reading is 0, ammeter reading to be 0, that means no current here. So, there is no current flowing through this part. What is the meaning of that? If there is a current, if there is a particular current originating from 12 volt battery, that current will flow through that R as well, that is all. Correct? It will flow through that R, and all that current will flow. We don't have to worry about the middle part really. We don't have to worry about the middle part. You know why? Because we can apply the Kirchhoff's law for the outer loop. Correct? If I mark this as A, B, C, D, E, F. So you can say you're going to apply the equation for A, B, C, D, E, F, A. What direction? Clockwise. You can apply sigma E equals sigma R, IR, sorry, sigma IR. Sigma E for the, I'm considering the outermost loop. If you want a better clarity, I will just highlight that loop like this. We are focusing only on the outer loop. So, the middle part is not our concern. You have to consider the batteries and the resistors only within the loop of consideration. We are focusing only on the outer. So, this is why I wanted to explain you certain samples from past papers and prototype papers. So that in future, no, you don't have to put this as I1, I2 and I3 and waste your time. Sigma E for the loop we are considering in blue color, it's just 12 volt, 12, nothing else. This battery we don't have to consider because it's not within the loop we considered. Sigma IR, current I is flowing through few resistors. What is it? I into 1 ohm plus I into 7 ohm. Here this 7. Anywhere else? And I into R. I into R. So that is 1. Okay, that is 1. So we have two unknowns, no? I is unknown, R is also unknown. Then we need another equation to solve this. No problems. We will be able to solve it. No issues. Then if I write the equation like this, what am I getting? I'm getting 12 equals I plus 7I, 8I plus IR. I have one equation now. Okay. Then what you can do is you can apply the equation. Now there are two unknowns. I need R or I. Then let's apply the equation for this part. Remember, there is no current going through this. If there is no current going through this resistor is useless because no current. Remember, if there is a resistor in your circuit and if there is no current flowing through that circuit, resistor, that resistor can be ignored. So what I'm going to do next is I need another equation, people, because I have I have two unknowns, I and R. Now I'm going to apply the equation for the bottom loop, that is B, C, D, E, B. When you apply the equation for the bottom loop, what's going to happen? Sigma E equals sigma IR, and I have considered the counterclockwise direction, and the battery is also in that counterclockwise direction. So you can put 4 equals sigma IR. Only IR is there, correct? This 4 ohm will not be taken into consideration, and there is no internal resistance for 4 volt as well, right? So we are getting 4 instead of 4 IR. IR is equal to 4, right? If I consider the first equation now, 12 is equal to 8I plus, instead of IR you can put 4. So 8 is equal to 8I, therefore I is equal to 8 over 8. What is the final answer, people? 1 ampere. I is 1 ampere. Done. And we know 4 is equal to IR. So 4 is equal to 1 into R. Therefore, final answer for R is going to be what? 4 ohm. That's it. Hence, the answer for this question is the second one. Can I see raise of hands if you understood this? So, if they have mentioned current, the reading of an ammeter is 0, you can just mark the current through that path as 0. That's all. Mark the current through that path as 0, and you will definitely have one unknown I, and then they have given another unknown resistor. So, two unknowns, get two equations and do it. If you want, you can apply the equation for the upper loop as well, but when you put it to upper loop 12, oh, everything is involved now, so I didn't want to apply it. I just wanted to apply it for the bottom loop, so that less number of components, easier for simplifications. Okay, so good that we did this question. This was different from the questions we discussed. So, the past paper questions are not very complicated as the questions, not very complicated in the sense they are not like detailed. We don't have way too many unknowns. Yeah, no. Through 4 ohm also, 4 volt also no current will flow, because 4 volt and R are in series. No? 4 volt and 4 ohm and 4 volt and this ammeter are in series. If they are saying that the ammeter reading is 0, that means there is no current flowing through this as well. There is no current through this path. It's possible. Right? Done. So, we are done with that first question. Just mark the information and then apply Kirchhoff's law. And then the next question regarding Kirchhoff's law, potential difference of the ends. Okay, what about this question now? So, then how can we apply Kirchhoff's law for second loop? Who is asking that question? No, that's okay. Even if current doesn't flow through that, that's fine. Even if current doesn't flow through that loop, yeah, even if even if current doesn't flow through that loop or the battery, that's okay. That doesn't matter. That's fine. You first mark the information. You mark the information and then you just apply the law. It doesn't matter whether the current is flowing through this or not. When you say loop, it doesn't mean the current should complete the loop. It's just that box we are talking about. Understood? So, don't think that the current must complete that cycle. No, it's not necessary. You just mark everything, and when I say a loop, you just take a box and then you just apply the law. Okay, right, good. If you have doubts like that, get it clarified, because Kirchhoff's law is not as tough as you think it is. Sometimes it can be very simple and it will save you a lot of, you can save a lot of time if you apply it in a smart way, rather than just taking way too many unknowns and spending unnecessarily excess amount of time. Okay, sorry, then we'll move on to the next one, that is question number 44. I think that also we can do it using Kirchhoff's law. Let's read the question carefully. If the potential difference of the ends of cell B is 0, okay, potential difference of the ends of cell B is 0, R is equal to, right, okay. Once again, just a single loop, let's put current coming out of the battery is I, so that current will flow through the resistor R, and the same current will go through battery okay, ER2 as well. This is the important part. I will underline it a different in red color maybe, yes. What are they saying? If the potential difference of the ends of cell B is 0, that means this is given as 0. Can someone tell me the equation for this potential difference? We have learnt it. We learnt it last week. What is it? What is the equation for the potential difference across a battery which has an internal resistance? Let's see who can remember. What is the equation? See, the current is coming out I. So, VB is equal to what? Hurry up. VB is equal to E minus IR. VB is equal to E minus IR. Hope you can remember that. So, instead of VB, I can say E minus IR2, correct? E minus IR2, and in the question they have told VB is equal to 0. They have mentioned VB equals 0. VB means the potential difference across the ends of the cell. So that's something we discussed last week. Hope you can remember. When there is a, no, I will put the summary of that. When there is a battery with an electromotive force of E and internal resistance of R, simple R, and if there is a current of I, a current I is coming out of it, the potential difference across the battery V is given by what? V is given by E minus IR. Understood, people? I think we did this last week, right? So that's where I have started. So if VB is equal to 0, let's start with that and get some information. Now they are saying VB is equal to 0. If VB is equal to 0, we know E minus IR2 according to the diagram is 0. That means E is equal to what? IR2. E is equal to IR2. I have an equation now. Because in the answers E is missing, capital E is missing. Now for loop, let's apply Kirchhoff's law. For loop, Kirchhoff's second law. Kirchhoff's second law. What is the equation? Sigma E equals sigma IR. There is only one loop, there is no point of naming it. Let's apply it clockwise. So there are two batteries. Should I add them or subtract them? E and E. Tell me quickly. Should we have to subtract? We have to add them. E plus E. What's the reason? Because plus of this battery is connected to minus of this battery. So they must be added. E plus E. Both are in the same direction. E plus E. And on the other side, the current is flowing through. Same current I is flowing through two resistors. R1 and R2. So I have to put I R1. Oh no, three resistors. In fact, three resistors. No? I R2 plus the big one, IR. I capital R. All right. So E plus E is actually 2E and 2E, and here we have, I can take I out as common. So I will be getting simple R1, simple R2 plus capital R. But we just figured out a little while ago, capital E is equal to IR2 according to the question. I mean, not according to the question. According to question, the potential difference across this battery is 0. So from that we found out that. Therefore, for capital E, I can substitute that value, that is 2 IR2. It's going to be equal to I times R1 plus simple R2, simple R1 plus simple R2 plus capital R. The good news is I will get cancelled out. I will get cancelled out. Therefore, we will be getting what? We will be getting 2R2 equals R1 plus R2 plus capital R. Correct? So, people, I can take this to the other side. I will be getting 2R2 minus R1 minus R2, that is capital R. Then what is the final answer? So, capital R is equal to 2R2 minus R2 is R2 minus R1. Hence, the answer is second. See how cool this is? Kirchhoff's law once again. Can I see a raise of hands if you understood this explanation, please? For that, they are combining two things. So you can't expect the question to be only based on Kirchhoff's law. It could be based on other things as well. It could be based on other things. Now this part, if you can't remember, then you can't do this question. If you don't figure this out, you will never be able to do this question. So make sure that you are thorough with everything. Done. So that is another question from 2016 prototype paper. Two questions and both were good. Right, fine. Then we'll move on to the next question. Can we do this one? No, we'll come back to that later. How about this one, people? No, I will explain those things later. Right. Okay, this one to 2020. Let's go with 2020 because our target here is Kirchhoff's law questions. So we'll do all these questions. Don't worry. But first, let's focus on Kirchhoff's law because today's lesson is Kirchhoff's law. Right. Next question comes from year 2020. Using a two-way key, K, two-way key means you can put it here or here, right? A cell of EMF E and internal resistance simple R can be connected in series either with resistor of resistance 8 ohm or 2 ohm. if the power dissipation of each resistor is the same, okay, what would be the value of internal resistance simple R? This is Kirchhoff's law plus power. Now we have done power dissipation in resistors. What is it? I squared R. That is the only equation. I'll just add it as an additional information. Power dissipation in resistor. Power dissipation in a resistor is given by the following equation. Is given by I squared R. I is the current through the resistor, R is that resistance itself. So they are going to put the two-way key to upper point and the bottom point, and during both the times, if the power dissipation of each resistor is the same, when they say each resistor, I think they mean 8 ohm or 2 ohm each resistor. So when you put it to 8 ohm, it has a certain power dissipation on it, and when you put it to 2 ohm also, we have the same power dissipation. I hope you guys can remember this graph we learned. Can you remember this graph, people? Tell me how many of you can remember this graph. Wait a minute. We learned a graph like this. The graph for power and the graph of power and what? Power and external resistance. Power and external resistance. You put it as capital R. Hope you can remember. The shape we got was like this. This is how it was. Can someone remember what this value was? Okay, you might have to unmute and speak. I can't see your chat. I'm sorry, it's covered from this white part at the bottom. What was this? Anyone?
Simple R?
Yeah, good. This is equal to simple R. When the external resistance become equal to simple R, you will get the maximum power. Salma, can you remember the equation for maximum power?
Yes, sir.
Yeah, what is it?
E squared over 4R.
Yeah, very good. Very good. E squared over 4 simple R. That was the equation for maximum power. Right? That is when you have, I mean, it should be, we are talking about a circuit like this. There must be a circuit like this where you have an external resistor R and E here and simple R here. Now, why am I talking about this? This is the reason. You can have equal power for two different values of capital R. See? R1, R2. In this case, according to the question, 2, and when the resistance is 2 ohm and 8 ohm, they are saying the power dissipation is equal. Correct? 2 ohm and 8 ohm, you are going to get the same power dissipation. If you are wondering, okay, how can that happen? If you are wondering how can we have the same power dissipation, here is the proof. So you can have the same power for two different values of resistors because of this graph. So this is how you should learn physics. You should have an understanding about everything. Everything is interconnected. Everything is interconnected. So you have to revise the previous lessons before you study a new lesson. Otherwise, you will be in trouble. Okay. So we don't have to bother about the maximum power or anything in this question. In this question, they are expecting you to figure this out. Now, this question is not hard at all. Very simple. First and foremost, what you have to do is you have to put K to 8 ohm. So let's put that K to 8 ohm. If I put K to 8 ohm, what will happen to 2 ohm? Anyone? What will happen to 2 ohm? Again, I can't read your messages. I'm sorry. I want you to tell me what will happen.
It won't work.
It will not work. It will not work. In other words, no current will flow through it because the circuit is incomplete, isn't it? The circuit is incomplete. Circuit is incomplete. Therefore, this is like worthless because there's no current. For current to flow, we need a completed loop. Here, there's a gap. So, no current will be flowing through this. Therefore, it's useless. Current is 0 through this. Let's take the current flowing through this circuit now as I1. We don't know what current is going to flow because there are few unknowns now. Say current I1 is flowing. What are we supposed to find out? Okay, we are supposed to find out the internal resistance. No? Okay, current I1 is flowing now through 8 ohm. Remember, I1. 2 ohm is not going to work. So, few things. Number one, power dissipation on power dissipation of 8 ohm. What is the equation? It's going to be I squared R, and in this context it's going to be I1 squared into 8. I1 squared into 8 because it's 8 ohm. Then finally we can say 8 I1 squared. 8 I1 squared. And furthermore, let me apply Kirchhoff's law, sigma E equals sigma R, sigma IR actually, sigma IR. So sigma is E is the only battery here, E. And for IR, what should I put, people? For IR, I think I have to put what? 8I1 plus I1R, correct? If not, I will write it this way. I1 into R, current is going through R, and current is also going through 8 ohm. I1 into 8. So finally, E is equal to, you can take I1 as common, it's going to be simple R plus 8. Right, so this is where we are going, this is the first equation we have, right? This is one equation, this is one. Okay, good. And we have to do the same analysis after you put the switch to the other one, correct? So let's put the switch to the other one quickly. Let's put the switch to 2 ohm. When you put the switch to 2 ohm, what's going to happen now? 2 ohm, this 8 ohm is not going to work now. 8 ohm, it is not going to work. Sorry, 8 ohm is not going to work. 2 ohm will work, but a different current is going to flow through that, because we can't expect the same current to flow. Tell me the reason. Because people, resistors are different now. Total resistance will be different in the circuit. So let's take that current as I2. Don't worry, we will be able to find out I2 and I1. You don't have to, you don't worry about that. It's very simple. We are almost there. So I2 is going to flow, I2 is going to flow, I2 is going to flow like this. Right, now let's do the same thing we did for the previous one. Power dissipation of 2 ohm. Power dissipation of 2 ohm this time. Power dissipation of 2 ohm. Okay. What is it equal to? It's going to be equal to I squared R. Once again, I squared R. I squared R is I2 squared into 2 this time. Therefore, it is 2 I2 squared. 2 I2 squared. And then for this circuit, if you apply Kirchhoff's law, sigma E equals sigma IR, what do we get? Sigma E is E once again. I2 current is flowing through simple R plus I2 current is flowing through 2. Therefore, finally, I will be getting E equals what? I2 common within bracket simple R plus 2. So I have two equations, 1, 2. How many unknowns do we have, people? We have 3 unknowns. One is capital E, one is simple R, and then we have 4 unknowns actually, the currents I1 and I2. Okay, but these are the information these are the pieces of information we can extract from what they have mentioned. They are putting K to the upper slot and they are putting K to the bottom slot. When you put K to the upper slot, 2 ohm won't work, current will flow through 8 ohm only. When you put it to the lower slot, 8 ohm won't work, current will flow through 2 ohm only. But this part, if the power dissipation of each resistor is same, that's important. If the power dissipation, if power dissipation of each resistor is the same, right? I'll write that green color part here. What is it? Power dissipation of 8 ohm is equal to power dissipation of 2 ohm. 8 ohm, it is what? 8 I1 squared, yeah, 8 I1 squared. For 2 ohm, it is 2 I2 squared. So from that one, I can figure out I1 over I1 squared over I2 squared is equal to what? 2 over 8. 2 over 8, which is 1 over 4. So I1 over I2 is how much? I1 over I2 is half. I1 over I2 is half. And I think I can get this fraction one more time. How is that? I can get this same fraction one more time if you divide first one by second one, correct? If you divide the first one by second one, or if you equate them first and second, you will be able to get the answer, because in the first and second only we have simple r. Let's do that quickly. Yeah, let's do that quickly. Give me a second. I hope we can manage the space. Right, so let's equate 1 and 2. Fine, I equate 1 and 2 because 1 and 2 both are equal to capital E. So it's 1 equals to 2, and that will give me I1 times r plus 8 equal to I2 times r plus 2. And if you simplify that, I will be getting I1 over I2 on the left side equal to r plus 2 over r plus 8 on the right side. People, I1 over I2 we know that is half. Half equals r plus 2 over r plus 8. What should I do? Cross multiply it. What do we get? R plus 8. R plus 8 equals 2r plus 4. That means final answer r is equal to 4 ohm. R is equal to 4 ohm, isn't it? We're getting r is equal to 4 ohm. Perfect. So this is a question which helps you revise the concepts about power dissipation in a resistor, Kirchhoff's law. That's it. Very simple. Stick to basics. Read the question carefully. Highlight the important parts and understand that, and then apply the basic concepts. And the Kirchhoff law, when you apply Kirchhoff's law, see how easy it is. Simplifications and all are very easy. Some of the questions we did, we just randomly put numbers. It was a little complicated, but here it's easy. So these questions, it's all about understanding. The simplification and applications will be very easy. But if you don't understand properly, then you will be in trouble. Okay, fine. So I have given you the explanation. Please try this again, and you can watch the YouTube streaming if you get it out. So that will be beneficial. Right, so that is the question from 2020, one of the latest questions, 2020. Okay, done. So that's 2020 for you, and let's move on to the next part. Maybe we can try 1 or 2 questions. Can we do this one? Yeah, we can do this one also, but yes, yeah, we can try this one. I have explained these questions about resistor combinations in another tutorial. I think I shared the link with you. You can watch it. So this one, another question from the same year, 2020, but it's the 14th MCQ. Yeah, it has a capacitor there. You can see there's a capacitor. So there are questions, many questions with which includes a capacitor as well as resistors in the circuit. Let's see how we are going to handle this question. Right. All batteries shown in the circuit diagram have negligible internal resistances, so we don't have to worry about internal resistance here. If the capacitor C is ideal, what is the potential difference across C? So that means it will not allow current to flow through it. Number one, no current flows through this one. No current flows through capacitor, so I can say I is 0 here. No current flows through this. I is 0. Alright, I is 0. The question is, what is the potential difference across C? So to find out the potential difference across C, you need to know the potential here and you need to know the potential here. You need to know the potentials at these 2 points. If it is 8 and 6, the answer is 2. If it is 8 and 7.5, answer is 0.5. If it is 8 and 4.5, for example, it will be 3.5, something like that. I think we have done, right, how to identify the potentials at each point. We have done that. For that, we will need to know the current through the circuit. So there's going to be one current flowing through the circuit, I, because when the capacitor has reached steady state, it will not allow current to flow through it. That's something universal we have to remember. Current will flow. So there's a current in the outer loop. There's going to be a current in the outer loop. So I'll highlight that part separately to show that current is going to flow only in that loop. Is it necessary? But never. Okay, we'll do it. So current is flowing only in the highlighted path, like this. Okay. Now let's quickly apply Kirchhoff's law for that loop. Sigma E equals sigma IR. What is sigma E, people? You have to be very careful here. The positive terminal of the batteries are connected to each other. Positive terminals of the batteries are connected to each other. Therefore, it should be subtracted, isn't it? It should be subtracted. Hence, you will be getting 6 minus 2 on the left side. And sigma IR, current I flows through 5 ohm and 3 ohm. So, I into 5 plus I into 3. Therefore, 4 here. On the right side, we have 8I. So, I is in fact equal to half ampere. Half ampere. Now, why am I finding that? Why am I finding that? Because I need to know how much potential is dropped across each resistor. Now, if I take this resistor, which is on top 3 ohm, let's say I want the potential drop across this one, V1. V1 is equal to IR. V equal IR. So, V1, I'll put V1, V equal IR. I is half and the resistance is 3. So, there is a drop of 1.5 volt across this one. Across this one, there is a drop of 1.5 volt. And how about this one then? Across this, how much is it going to be? Across this, let's take V2 equals again IR. I is half, resistance is 5. What is half into 5, people? 2.5 volt, right? Half into 5 is 2.5 volt. 2.5 volt is the potential drop here. And we have learned when we are supposed to find out the potentials, if there are no points grounded, then I can start with the largest EMF. So, this 6 volt, I am going to start here. This is, I am going to take the positive terminal to be at 6 volt of the battery and negative terminal to be at 0 volt of the battery, right? 0 volt. So, negative terminal of the battery to be 0 volt. This is where we are going to start, starting point. Hope you guys can remember this. You take the large battery with the largest EMF, then you take 6 and 0. If you take it that way, you will not get, it will be easy for you. If it is 6 volt here, here also it is 6 volt. Why? No resistor, capacitor, nothing here. Here also it will be 6 volt. Okay, carefully now tell me, someone will have to unmute and speak. I can't read your texts now. What is going to be the potential at this point? What's the potential at this point? Anyone? What's the potential at this point? We have done it before. What is it? 6. This is a 2 volt battery. So, what's the potential here? Hurry up, anyone? Come on. 6, 2 volt battery. What is it here? It's going to be 4 volt. 4. To the side of the positive terminal, to the side of the positive terminal, we will have high potential. To the side of the negative terminal, we will have low potential. The difference is 2. So, if it is 6 here, it will be 4 here. And 4, 1.5 is dropped across this one. So, what is the potential here now? 4 minus 1.5, 2.5. 4 minus 1.5, 2.5 volt. Okay, 2.5 volt. How did that 2.5 come? 2.5 we are getting. That came from this 4 minus 1.5, and then that 2.5 will remain here as well. 2.5, 2.5 here also, it's going to be 2.5 volt. Why is that? There's no resistor or anything here. 2.5 volt. Therefore, people, now we have reached one side of the capacitor. We have reached one side of the capacitor, that is 2.5 volt. What is the potential here? Here it's 6 volt. That means here it is 6 volt, obviously 6 volt. Okay, now someone tell me what is the potential at this point? Hurry up. What is the potential at this point?
3 volt.
Yes, very good. It's going to be 3 volt. Why 3 volt? Battery, its EMF is 3 volt. To the positive terminal side, it is 6. That means to the negative terminal side, it should be a lower potential, and the difference must be 3. So 3. Right, now we have the capacitor. Now we have the capacitor. On either side, we know the we know the potentials as well. So they are asking for the potential difference across the capacitor. That's the question, isn't it? So if we are done, we will one side the potential is 3 volt. The other side the potential is 2.5 volt. Therefore, what is the potential difference? The potential difference is 3 minus 2.5. 3 minus 2.5, and that is half. Can someone check the answer and confirm whether the answer is correct? 2020 14th MCQ. 2020 14th MCQ, half is the answer. First answer. Again, I can't read your texts, people. It will be better if someone can confirm it. You can unmute and see. Right, so very nice question. First, find the current. It's important because we need to know how much potential drop is there in each resistor, and then you do that thing we did in one of our previous classes. You choose none of the points is grounded. If there's no point grounded, you choose the battery with the largest largest EMF, and take the potentials on either side like this. The positive potential you take it as 6, the negative side you take it as 0, and then you continue. Right, anyone who has 2020 scheme, can you check it? 14th. Right, okay, take a screenshot of this. No.
Yes, sir, it's first answer.
Right, thank you, Krishnika. All right, fine. So that is another example of how to use Kirchhoff's law for you. Okay, do we have more time? Hope we have. No, it's almost 6, right? Time is going to be a problem, right? Fine, but give me like another 10 minutes maybe, because I want to show you few really important questions where you have to apply Kirchhoff's law really carefully. I mean, you can't, without applying it randomly, you have to apply it really carefully. Now, one such example is, now you can try the remaining questions, okay? You can try the remaining questions. Maybe we can discuss. In your Pesuru book, you have a section called Kirchhoff's law, combination of cells. So you can definitely try all those MCQs. But there are certain MCQs which require certain technique. Now, for example, this MCQ from 2012, how do we do it in a very simple manner with no complications whatsoever, right? The question here, 2012, they are saying, what is the current through 10 ohm? What's the current through 10 ohm? What's the current through 10 ohm? That's the question. So, people, what you need to do is, you have to see whether you can choose a loop which includes only that resistor. Okay, they are asking for the current through 10 ohm resistor, right? So, we don't have to take I1, I2, I3, no need. Try to choose a loop with only with the 10 ohm required resistor. If possible, if that has to be possible, right? If possible, a loop including only 10 ohm as the resistor must be chosen. I'll tell you why. Because when you consider current in the Kirchhoff's law equation, IR part, you have to worry about the current going through the resistors only, right? Fine. So here I will choose a loop, see if it makes sense. What about this loop? What if I choose this particular loop? I'm going to avoid 30 ohm and I'm going to choose this loop. The loop I am highlighting in red color. How many resistors there are in this loop? Tell me. How many resistors are in this loop? There's only one resistor. Correct? There's only one resistor. So we don't have to bother about what is going on with this 30 ohm. We don't have to worry what's happening with this 30 ohm. We can forget about it. Now apply Kirchhoff's law for the loop you chose. It's very simple after that. So for this loop, now there's going to be a current flowing through this 10 ohm. Let's take that current as I, right? That's enough, and the same current is going to flow through this, and until here it will flow. After that, we don't know what happens. We don't care because internal resistance here is 0. So for that loop, if you put sigma E equals sigma IR, now you have to be a little careful. Check the batteries. There are 2 batteries involved in that loop. How are they connected? Plus of this, minus of this. and minus of this plus. So plus is connected to minus. That means they must be added, right? Sigma E. So it's going to be what? 9 plus 6. And for IR, surprisingly, it will be only I into 10. That's all. We don't have to write 30 because 30 is not in our loop. It will just stay that way. So it is 15 equal to 10I. I is equal to 1.5 ampere. Simple as that. Answer is second one. So applying Kirchhoff's law in a smart manner, it's important because you will get the answer quickly and you will not just get stuck in the question with so many unknowns. Okay. So can I see raise of hands if you understood this application of Kirchhoff's law? Right. Now I will show you another quick example. And that is from year 2000. Wait, yeah, this one, 2009. Our paper, 2009. Okay. Right. Here also the same thing. You have to you have to use the same concept. What do you mean by same concept? Try to find a loop which includes only the required resistor. Let's read the question. In the circuit shown, the current through 150 ohm resistor is. Let's try to choose a loop which includes only 150 ohm as the resistor. So here also you can do the same thing. See now. What about this loop, guys? This one, this one, this one, this one, this one. Am I correct? Does it make sense? See, this is 100 ohm. I think this one is 100 ohm. There's a printing problem. This 100 ohm should come closer to that. I think there's another 100 ohm, but we don't have to worry about those. We just can forget about that. Yeah, this is 100 ohm, but that is not our problem. We don't care about the 100 ohms, 100 ohm resistors. Why? We want the current only through this one. So let's mark the current only flowing through that, and that's it. So again, battery plus here, minus here, and here minus and plus. So plus and minus are connected. When you apply Kirchhoff's law, they must be added. So for that loop I have chosen, let's apply sigma E equals sigma IR. Sigma E there is going to be 10 plus 5. Both must be added, equal to, for IR, surprisingly, you have to choose only I into 150. We don't have to worry about those 100 ohms because we have not included those 100 ohms in our loop. Then 15 is equal to 150 I is equal to 15 over 150, and that is 0.1 ampere, and the answer is third one. Okay, right. So Kirchhoff's law is not always I1, I2, I3, I4. No. Smart. Be smart. Try to figure out what they are expecting of you. Sometimes this might not be possible, people. Sometimes this might not be possible. If there is a resistor here, for example, you can't help. If this internal resistance has to be considered, you can't help. You will have to, take an unknown and do. But if there is a possibility that you can avoid all the other resistors and take only this resistor into the loop, then it's a jackpot. It's very easy. Done. Right. So I think that's enough for today. Please go through the other questions. Try as much as you can. See how many questions are there. So many questions. Only until 2016 there are 26 MCQs almost every year, almost from 1990 to 2016. Average one question per year is there, so you need a lot of practice. I don't think you will be able to do all of them. That's totally fine, but let's see how much. Try our best to do. Now, this question is a nice one. Kirchhoff's law. You can apply Kirchhoff's law and do this. This one also you can do it normally. All these questions you can do it normally. Now this is similar to that capacitor question we did. You guys can do it normally. So see how far you can go, and let's discuss